All right, the thought process you just went through is probably one of the most important thought processes required to be good at doing simulations, or really even just being a scientist. That thought exercise is completely general, and the answers that you came up with are probably true for a variety of fields. So, like the process of thinking about how to judge results is really something that extends to finite element analysis, finite volume analysis, so we'll learn about the difference, finite difference methods, molecular dynamics, so things that are kind of barely within mechanical engineering reach, density functional theory, and basically any piece of software generated to make a prediction. The ability to judge results, the methods that you use are not specific to the type of simulations that you're doing. The thought process that you just went through is called verification, validation, and uncertainty quantification. It has its own special track within the ASME subculture. So some specific terms, so there's some specific terminology there. Verification is really the process of checking that a numerical simulation that you did or somebody else did actually solves the model that it was trying to solve. So that means first and foremost that there are, of course, no bugs in the code, that it actually produces a result. But also that, like, when you go to look at, I asked it to do this boundary condition, or I thought I did, does the result actually reflect the fact that those boundary conditions were maintained? Does the solution, like if I have a continuous differential equation that my discretized problem is solving, does it actually solve that problem correctly? And at what point do the solutions not really depend on how I discretize the problem? So verification is really the idea of checking whether the numerical solution matches your model, which may not necessarily be a numerical model. It may be, partial differential equations typically. Validation refers to a different thing, which is whether the model that you chose is actually an accurate reflection of reality. So often we make a model of a system that is made out of differential equations or maybe partial differential equations, and we're not really sure whether that model is really a good description of the system, but we use it anyway because we got to simulate something. So validation is the process of going back to check that the results produced by your numerical model actually are a good description of the real physics that's going on. So typically this means that you have to compare against experiments. Validation does. And then uncertainty quantification refers to the concept that a numerical solution usually it will always provide you a result as long as you've done the verification step and you don't have any bugs. But the question is, like, how close should I expect that prediction that comes out of the model to be to either the exact solution, if you're like trying to replicate some continuous model, or to replicating the actual experimental ground truth. So this uncertainty quantification can really refer to either of those comparisons. But basically what you need to be able to do is look at a set of numerical results and judge essentially to what level of accuracy you trust them. Is it 1 digit, 2 digits, 3 digits, 4 digits, 12 digits? And I'll just mention that we often don't in academia teach people how to do the validation step. So we often just presume that these models that we create, like the diffusion model, the diffusion equation, and based on Fourier's law and other things, we often formulate our models and we don't really attempt to compare them to experiment. We sort of proof by intimidate students into believing that it's true. But in many real situations, including research and industrial situations, you're trying to model complex things. And the reason why you're trying to model them is often because you don't exactly know what's going on. And so they're difficult to model. And sometimes the simplifications you make in order to make a problem solvable mean that it's no longer actually solving the real problem. So trying to understand how to do that is actually a very important thing to do. I am mostly going to focus this talk on the verification step, making sure that you actually solved the model correctly. So if I'm trying to solve the diffusion equation, does the numerical solution I have actually do that accurately, and how accurately? So the uncertainty quantification step.